Okay, back again with the practical geochemistry data analysis exam. Feedback for question 3 for the 2019 exam. So again, this is the overall mark distribution, and we can look at the mark distribution for all of the questions here. So we're going to focus now on question 3 down in the bottom left, as I guess you are looking at it. And again, you can see a wide range of marks. I think quite a lot of people did a little bit better in this question than in the previous two. So good job on that. Well done for knowing your stuff and revising well. So we just go through this question quickly and look at the kind of stuff that we were really looking for. So we'll just put in here. Okay, so yeah, some people did well, some people not so well, which was true. Okay, so again, a question with many parts. Part A, when we're using radiogenic isotopes as a geochronometer, what are the assumptions we have to make? So this was kind of the first slide of the first lecture on the radiogenic isotope part of the course. There are 3 really fundamental assumptions. So knowing these is important. You could have maybe commented on also whether these are important or trivial assumptions, or are almost always true, or always true. Like the rate of radioactive decay is independent of all external influences. So through time, the rate of decay is constant. That is a fundamental assumption of using radioactive decay as a chronometer, and it is by far the best of all of the assumptions in science. So that'd be good to have written down. The next assumption that any change in the isotope ratio is due to decay and production of radioisotopes, and not by any kind of chemically induced fractionation. Now this isn't true. There is fractionation of isotopes by chemical processes. This is the field of stable isotope geochemistry, and that same isotope fractionation happens to radiogenic isotopes. Now, you can either make an assumption that this is small and can be ignored, or in some cases it's an isotope fractionation we can actually correct for. So there's that assumption. And then the last assumption is the one that's most often violated in a pleasant and annoying way for geochronologists, and that's of the assumption of a closed system. So this is that when your sample is formed, when the clock starts, you don't add or remove any of the parent or daughter isotopes. So you're basically keeping everything in a lockbox and not letting anything in or out except by radioactive decay. Now, sometimes this is true, or true enough to not matter, and in other cases it is not true, and we need to do something about that, or interpret our data in such a way that takes into account this open system behavior. And we'll come on to that towards the end of the question, where we ask that question. So those are some things that you should know. Okay, next part. I give you an equation because I'm nice, and here it is. So it is the equation for radioactive decay, and all I'm asking you to do here is to take these terms and tell me what they are. Okay, so we've got, I guess you basically have to match up these symbols. Options. Hands, we're going to match up these symbols. Euler's number, that's kind of like very easy to do that there. We've got maybe time here, that's probably, so that's that time there. Number of moles of the parent atom, so that's the parent is n. And the decay constant, that's lambda here. The total number of moles would be D here, and the total number of moles of the daughter isotope before decay commences. So this is the initial amount of daughter isotopes before you allow any decay happen. That's D0, which I will get to like this. gap. There we go. Okay, so you didn't have to draw this spidery mess of lines or all that kind of stuff. Just make a list of the things that are in the equation and what they are. Do that, get some marks, which I think most people did, which was great. I will get rid of this pointer. Okay. Ooh, now we've got laser pointer. Okay, so can I hide that up here? Yeah, I can. Okay, so for uranium lead dating, show that for an ideal sample, an age can be calculated from measurements of lead isotopes. So we'll come back to that phrase, an ideal sample. You could go into some discussion in your answer as to what an ideal sample comprises, what that actually means. I guess it does mean that, going back to the first part of the question, it fulfills all of those assumptions. So radioactive decay is constant. That's a really good assumption. That's almost all samples have that, even the non-ideal ones. There's no isotope fractionation due to stable isotope fractionation processes. And importantly, there's no gain or loss. So that's probably something we'll come back to in a bit. But the question is really asking, show that we can calculate an age, or an age can be got at somehow, from the uranium lead system by only measuring the lead isotopes, by not having any idea about how much parent isotope there was at the beginning, which seems odd. So this is our decay equation. So we're basically looking at the uranium lead. So uranium is our parent, N, and lead is our daughter isotope. And we're asking, can we work out this age, T, without knowing what N is? Which seems a bit, how can we do that? So we went through this in the lecture, or a lecture at least. So if we plug and chug our variables for uranium and lead into this, we can take the parent isotope uranium-238, decays to lead-206. That's our daughter isotope. So the 206 lead that we have at any time is equal to the 206 that we had at the beginning. That's that D0, plus that produced from radioactive decay of uranium-238. Okay, so that's this last part of this thing. Okay, so when we come now to mentioning this ideal sample part of thing, we're looking for something that not only will it contain all of these kind of radioactive isotopes so we can measure them, so some mineral that is good at holding on to these elements, but one that maybe forms and includes a lot of uranium, okay, because we want that to decay and be in our sample, and then decay, I guess, and it would produce some daughter products, but we want our sample to originally formed without any of the daughter in it. So we want a mineral that has got that is where uranium is compatible in that mineral, but lead is incompatible. Okay, a really good example of that is the mineral zircon. It's also a really robust mineral. It's very difficult to dissolve it in a magmatic system or anything like that. So it's very good at keeping on to its daughter products of all the trace elements inside. Yum, which is good. So this assumption that we make here, that we can just take away the initial lead from both sides of this equation here, it gives us this term here, which is the lead in our total amount of lead in our sample minus that which was there initially. So this is this 206 lead star. Now, if this initial lead was a very small number, then that's just the amount from radioactive decay. Okay, so there are some corrections we can do to actually correct for this, but in most situations we can assume that it's an insignificant contributor to our daughter isotope collection. Okay, so that gives us then this equation at the bottom, where we've got the 206 divided by the 208. So 206 lead divided by the 238 uranium is equal to this thing here, which has got E, it's got the decay constant, it's got time, the thing we want to calculate, and it's got So still, if we wanted to calculate an age from that equation, then we would still have to measure the uranium isotope. So that doesn't fulfill the answer to this question. Now, the important thing to be able to answer this question is that you have to be able to remember that the uranium-lead system, there are two decay chains. There's uranium-238 that decays to 206, lead, but there's also 235 uranium. It's another isotope of uranium that exists in the Earth and the universe more widely, and that has constantly decaying to form a different isotope of lead, the 207. Okay, so we could write another equation that is the same as the equation for the 238 to 206 decay, for the 235 to 207 decay. That's this one here. And they just have different decay constant because they are different parent isotopes that are decaying to different daughter isotopes. So with these two equations now, we can finally combine those together. We can divide one equation by the other, which will then ultimately give us something which is a lead isotope ratio, okay, that will change through time, okay, that is dependent on the uranium isotope ratio and this kind of equation here with time in it. Now, we don't need to measure the uranium isotope ratio because that's the same everywhere. That doesn't change. That's just a feature of our solar system, in that there is a certain amount of, at the beginning of the solar system, a certain amount of uranium-238 and 235. They've been decaying ever since, so they've been, now they are that ratio that they are, which is 137.88, I think. Anyway, didn't need to know that. All you need to know is that you don't need to know it, if that makes sense. And the other thing is that we've now got an equation which has got t in it, so we can work out time. Now, this is an equation that you can't actually solve analytically, but we can use a computer to solve it iteratively if we so choose. So that would have got you some marks. Okay, so the last two parts really asking you to draw some of the graphs of the uranium-lead system to show how we can use measurements of uranium and lead to check the assumptions that have gone into that previous age calculation. So question asks you to just draw a graph so that we can use to show that the assumptions of a closed system, so that we haven't lost or gained any parent or daughter isotope, they're true, and therefore we can use the approach in part C to calculate the age. Okay. And some little, I guess, clues in the question as to what we want. So we want you to sketch a graph, okay, and that graph should have element ratios and isotopes on the graph. So if you didn't have element ratios on the axes of your graphs, then marks lost. So this really is what we're looking for. So we've got the two decay systems here. We've got the uranium-238 decaying to 206, lead on the y-axis here, so lead 206 divided by 238 uranium, and the 207 lead to 235 uranium on the x-axis. Now, if a sample formed initially with no lead in it, lots and lots of uranium, then these ratios would be very, very low. Okay, so we'd start out somewhere near the origin of the graph because the mineral would form with uranium in it, but no daughter isotopes. And then over time, as this sample gets progressively older, then it will follow this red curve, which is the Concordia, which is dependent on the rates of decay only between uranium-238 and uranium-235. Okay. So if a sample has not lost or gained any parent or daughter isotope, then and it's only changed its uranium content and lead content by the process of radioactive decay, then it will fall somewhere along this red line. And the older it is, the further up towards the top right it will go. Now, if for any reason we lose, let's say, for instance, we were to lose uranium, okay, so something leaches just uranium out, that will make these ratios go up because we're reducing the amount of uranium, so that will force us off in this direction here. If we gain uranium, it will force us back down towards the origin. And similarly for lead. Okay, if we lose lead, then that will make these ratios smaller and we'll head down towards the origin. If we gain lead, then we'll shoot off to the top right again. So we can use this as a check of the assumption of a closed system. Okay, so that's kind of important. And then the last part of this question is basically to do another sketch and explain how we can use that kind of graphical arrangement to calculate ages where this assumption of closed system is not is not met. So where we might have lost or gained some kind of lead from our samples. So what we're looking for here is this guy, where if we measure a suite of samples that have all from the same kind of rock, they've undergone like the same number of geological events, they were formed at the same time, they might have undergone metamorphism at the same time. But during that process of alteration, they might have lost or gained different amounts of the uranium and lead. And what that means is that we'll have an array of samples that will kind of point away from their true age back down towards the origin if they were altered very recently. But if after losing that lead gets to build up again over time as a subsequent decay of uranium, they will point towards the age of the metamorphic event. Okay. So that's something that you could have done, which would have been fun. A few people drew the graph or sets of graphs from the rubidium strontium system, showing how you can use that to get multiple different ages from either bulk rock or mineral separates. And that's kind of correct, but it's not relevant to the uranium lead system. So this is what you should have done, but you did get some credit for that slightly misdirected answer of that one. Anyway, so fun times. Right, so there you go. Some people did very well, some people not so well. Most people did really well on this question, so good job. Yeah, so I guess again, stay tuned for part 4 of the geochemistry feedback video, which is in a playlist near you somewhere. Yeah. Oh no, I'm on the wrong thing. Oh no, how do I? Yeah.